Have you ever stopped to think about why nothing in the universe can travel faster than light, and what that really means about the fundamental nature of the reality we live in? Because when Neil deGrasse Tyson explains this concept, he always emphasizes that we are not just talking about an arbitrary speed limit, like a cosmic road sign saying, "Do not exceed 200,000 kilometers per second," but rather something much deeper and more disturbing about the very fabric of space and time. What if I told you that the speed of light is not really about the light itself, but about something so fundamental that it defines the way cause and effect work throughout the universe? Something that determines whether the past, present, and future make sense or whether everything turns into absolute chaos? Can you imagine a universe where this speed did not exist? Where you could send a signal to the past and answer yourself before even asking the original question, creating impossible paradoxes that would break the logic of existence, because that is exactly what this cosmic limit prevents. And when Tyson explains this, he likes to start with a question simple that makes us rethink everything we thought we knew. He asks why, when we look at the stars, we are literally looking into the past, and why this is not just a poetic curiosity, but an inevitable consequence of this fundamental limit. Imagine you are in a spaceship traveling through the cosmos, and you decide to accelerate more and more, using more and more powerful engines. You keep accelerating, burning fuel, applying force, and your speed increases more and more. You go from 10% of the speed of light to 20%, then 50%, then 90%. And you think just a little more acceleration, and I'm going to go over that limit. But here's what Neil deGrasse Tyson wants you to understand. No matter how much energy you add, no matter how powerful your engines are, no matter how long you accelerate, you're never going to reach that final speed. It's as if the universe is conspiring against you in increasingly bizarre ways the closer you get to that limit. And it's not because there's an invisible wall or a mysterious force pushing you back, but because the very nature of mass, of energy, of space and time changes as you speed up. And if you are one of those who love unraveling the mysteries of the cosmos like me, subscribe to the channel because we have many more fascinating scientific revelations to share with you as we explore the limits of what is possible in the universe. Now let me tell you how we came to this disturbing understanding, because the story begins long before Einstein. It begins with astronomers observing the moons of Jupiter in the 17th century. Ole Rømer was observing Io, one of Jupiter's moons, orbiting the giant planet, and noticed something strange. Io's eclipses happened earlier or later depending on where the Earth was in its orbit around the Sun. When the Earth was closer to Jupiter, the eclipses happened a little earlier. When it was further away, they happened a little later. And Rømer had a brilliant intuition. Light does not travel instantly. It takes time to traverse space, and the difference in the times of the eclipses was the time. This is how we first measured the speed of light, discovering that it traveled at approximately 300,000 kilometers per second, a speed so absurdly fast that it seems instantaneous in our everyday experience. When you turn on a lamp, the light fills the room so quickly that it seems instantaneous. But on the cosmic scale, this speed creates significant delays. Light from the sun takes 8 minutes and 20 seconds to reach us, meaning we see the sun as it was 8 years ago. Minutes. If the sun exploded right now, we wouldn't know until 8 minutes later. The light from the nearest star, Proxima Centauri, takes 4.2 years to reach us. We see this star as it was 4 years ago. Distant galaxies that we see with our telescopes existed millions or billions of years ago. We are literally looking into the past of the universe. And this is not just an astronomical curiosity, but a profound revelation about the nature of time and observation. Think about it. When you look at someone on the other side of the room, you are seeing what they were like a few nanoseconds ago. The difference is so small that it is irrelevant, but still technically true. When you look at the moon, you are seeing what it was like a 0.3 seconds ago. When we look at Jupiter, we are seeing between 30 and 50 minutes in the past, depending on the relative positions of the planets. Granddaughters, and the further we look, the deeper into the past we travel. The most powerful telescopes can see galaxies so distant that their light was emitted when the universe was only a few 100 million years old. We are literally seeing the infancy of the cosmos. But for decades after Romer, scientists thought that light was just another thing that traveled through space, just as sound travels through air or waves travel through water. They assumed that there must be a medium through which light traveled. They called this medium hypothetical luminiferous ether, an invisible substance that would permeate all of space, filling the void between the planets and the stars. And if light traveled through the ether, then it made sense to think that we could measure our speed relative to this ether, just as you can measure your speed relative to the air when you are flying in an airplane, or your speed relative to the water when you are swimming. Two scientists called Albert Michelson and Edward Morley decided to do just that. In the late 19th century, they constructed an incredibly accurate experiment to detect the movement of the Earth through the ether. The Michelson-Morley experiment is considered one of the most important experiments in the history of physics. The idea was simple but ingenious. They used a device called an interferometer, which split a ray of light in two, sent the rays in perpendicular directions, reflected each one back using mirrors, and then recombined them. If the Earth was moving through the ether, then one of the rays should travel partially against the flow of the ether, while the other traveled perpendicular to it. This would create a small difference in time that each ray would take to complete its journey. And when the rays were recombined, this difference in time would create an interference pattern that would be detectable. It is like swimming in a river. You swim faster with the current than against it. So Michelson and Morley measured the speed of light in different directions, hoping to see a difference that would indicate our movement through the ether. But here is what shocked them to the core and shook the foundations of physics. There was no difference at all. Light traveled at exactly the same speed in all directions, regardless of how the Earth was moving, regardless of the time of day, regardless of the season, regardless of any factor that could affect our movement through the supposed ether. This made no sense whatsoever according to the physics of the time. It was as if you were on a moving train and threw a ball forward and discovered that it travels at the same speed relative to the ground. No matter how fast the train was going, it was absurd. It violated everything we understood about relative motion based on Newtonian mechanics, which had worked perfectly for 200 years. Some scientists tried to save the ether theory by proposing that perhaps the Earth was dragging the ether along with it. But other astronomical observations contradicted this. Others proposed that perhaps objects moving through the ether contracted in the direction of motion by just the right amount to hide the effects. George Fitzgerald and Hendrik Lorentz developed this idea mathematically before Einstein. But they had no physical explanation for why this would happen. It was just an ad hoc fix to make the theory work, and that was the great crisis of physics that was waiting for someone with the courage to rethink the foundations of reality. Someone willing to abandon assumptions that seemed so obvious that no one questioned them. And that person was Albert Einstein in 1905, when he was just 26 years old and working as a patent examiner in Bern, Switzerland. But here is what Neil deGrasse Tyson always emphasizes about Einstein, and that is crucial to understanding not just history, but the nature of scientific discovery itself. He did not solve this problem by finding a complex explanation, or inventing a new force, mysterious, or by adding layers of complicated mathematics on top of existing physics. He solved it by doing something much more radical and revolutionary. He simply accepted the experimental result at face value and followed the logical consequences wherever they led, no matter how bizarre or counterintuitive. He said, "What if the speed of light is really constant for all observers, no matter how they are moving?" And if we take this seriously, absolutely seriously as a fundamental fact of nature, what does this mean for our notions of space and time? Because if the speed of light is always the same for everyone, so something else needs to change. Something that we assume to be fixed and absolute must in fact be flexible and relative. And what changes are space and time itself? This is the great revelation of relativity, and this. Special space and time are not fixed, and absolute stages where events happen independently of each other. They are flexible, malleable, dynamic, intertwined in a single four-dimensional structure called space-time. They stretch and compress, depending on how you are moving. And when I say they change, I am not speaking metaphorically or philosophically. I am speaking literally and physically. When you are traveling very fast relative to someone else, time literally passes slower for you. This is not an illusion or a trick of perception or a psychological effect. It is real, measurable, experimentally proven. Countless times since then, clocks on moving planes actually keep less time than clocks stationary on the ground. This discovery impacted scientists all over the world. When it was experimentally verified for the first time in the 60s, using extremely accurate atomic clocks flying around the world on commercial planes. And I wonder, from where you are watching now, comment on your city or country. It is incredible to think that we are all connected in this same universe, trying to understand it better while we explore how time itself can pass at different speeds, depending on where we are and how we are moving. And this idea that time is relative, not absolute, is so profound and challenging that even today, more than a century later, many people have difficulty really accepting it viscerally. We can understand the math, we can see the experimental evidence, but it still feels wrong because it contradicts all of our intuitions developed in a world where we move so slowly compared to the speed of light that these effects are completely imperceptible. Astronauts on the International Space Station, who orbits Earth at approximately 8 kilometers per second age, slightly slower than people on Earth. The difference is minuscule, perhaps a few milliseconds over months in space, because even 8 kilometers per second is only 0.0027% the speed of light. But it is detectable with atomic clocks that can measure time differences of billionths of a second. And when astronauts return, their clocks are slightly behind compared to clocks on Earth. They have literally traveled to the future by a split second. Now let's go deeper into this idea because it gets even weirder and more fascinating when you start to examine the implications. When Einstein realized that time is not absolute, he also realized something equally disturbing about space. Distances are not absolute either. If you are traveling really fast in a spaceship and you pass me while I am standing still, from my point of view, your ship appears shorter in the direction of motion. It literally contracts. It is not that it is being compressed by some force or that the material is being crushed, but from a space-time perspective, the very length of the ship in the direction of motion is shorter. And from your point of view, inside the ship, you don't feel anything strange. You don't feel like you are being crushed. The objects inside the ship appear normal to you. But when you look outside and measure the distances through space, you find that they appear shorter in the direction of your movement. It is as if the universe compresses in front of you as you move through it. This is called Lorentz contraction, named after Hendrik Lorentz, who derived the equations mathematically, even though it did not have the correct physical interpretation, and it is not an optical illusion caused by the way light travels. It is an actual change in the geometry of space-time. Different observers literally measure different distances between the same two events in space-time, and both are correct within their own frames of reference. There is no one privileged frame of reference that has the true measurement. All measurements are equally valid as long as you specify which frame of reference you are measuring from. And here is where it all connects in a way mathematically beautiful and profound that still gives me goosebumps every time I think about it. These distortions of space and time are not bugs in the universe, or design flaws, or random inconveniences. They are fundamental features. They are exactly the properties needed to ensure that the speed of light remains constant for all observers. Think of it this way. Speed is distance divided by time. If you are traveling very fast and time is passing slower for you, and distances are contracting in front of you, when you measure the speed of light by dividing the distance the light traveled by the time it took, the changes in distance and time cancel each other out perfectly in such a way that you still measure light traveling at exactly 300,000 kilometers per second. It's a mathematical symmetry. The speed of light is not fundamentally about light. It just gets its name for historical reasons because light is how we discovered it. But it is really about the structure of space-time itself. It is about the maximum speed at which information can travel through the universe. It's about the speed at which cause can take effect. It's about the rate at which events in one place can influence events in another place. Modern physicists often don't even call it the speed of light. They call it the speed of causality, or limiting speed, or the structural constant of space-time. And it turns out that light travels at that speed not because there's anything special about light itself, but because photons have no mass, and anything without mass must travel at the maximum speed of the universe. It's a necessary consequence of the structure of space-time. Other massless particles like hypothetical gravitons that would transmit gravitational force would also travel at that same speed. And in fact, the gravitational waves that were first detected in 2015 travel at exactly the speed of light, confirming that gravity also propagates at the universal limiting speed. But speed itself is a property of space-time, not of any specific particle traveling through it. And here's the part that really blows the mind when you stop to think about it. This speed shows up in the equations of physics in surprising places, and apparently unrelated things that have nothing to do with light. It appears in the relationship between energy and mass in the famous equation E equals mc squared, where CE is the speed of light. But the equation is actually saying something profound about the equivalence between mass and energy. It appears in Maxwell's electromagnetic theory, which was developed before relativity. Maxwell derived from his equations that electromagnetic waves should travel at a specific speed, and when he calculated this speed, he discovered that it was exactly the speed of light that had been measured. This is how we realized that light is an electromagnetic wave. But the fact that this same speed appears in such different contexts suggests that it is something truly fundamental. It appears in quantum mechanics when you calculate how particles behave at high energies. It appears in string theory when you try to unify all the forces of nature. It appears in practically any fundamental physical theory we try to construct. It is as if the universe has a fundamental speed built into its most basic architecture, a speed that governs absolutely everything. From the behavior of subatomic particles to the evolution of galaxies, and when you try to accelerate something that has mass to that speed, something extraordinary and profoundly revealing happens. The faster you go, the more energy you need to accelerate further. And it is not a linear increase where you need twice as much energy to go twice as fast. It is exponential. The energy required grows dramatically as you approach the speed of light. When you are at 10% the speed of light, your effective or relativistic mass has increased by only 0.5%. It is a small but measurable effect. When you are at 50% the speed of light, your effective mass has increased by about 15%. When you are at 90% the speed of light, your effective mass is more than twice your resting mass. When you are at 99%, the speed of light, your effective mass is 7 times greater. And as you get closer and closer to the speed of light, 99.9%, 99.99%, your effective mass grows exponentially towards infinity, which means that you would need infinite energy to actually reach the speed of light. It is physically impossible. It is not a technological limitation that we can overcome with better engineering or with more advanced materials or with more powerful reactors. It is a fundamental limitation of reality itself. It is like trying to divide by zero or create a square circle or build a staircase that leads out of the universe. It just doesn't make sense within the operating rules of our cosmos. The equations literally generate infinity when you try to put the speed of a massive object equal to the speed of light. And in physics, when your equations generate infinity, it usually means that you're trying to do something impossible, or that your theory has broken and needs to be replaced. But in this case, the theory hasn't broken. It's telling you that you've reached a fundamental limit. And Neil deGrasse Tyson likes to explain this using an analogy that really helps build intuition. Even if it's not perfectly accurate in all the technical details, imagine you're driving a car and your speed is indicated on the speedometer. Now imagine that as you accelerate, the very fuel you're using to accelerate becomes heavier. Not metaphorically, but literally heavier with more mass. The faster you go, the faster the fuel gets heavier, so you need more fuel to accelerate the same amount. But this additional fuel also gets heavier as you accelerate, so you need even more fuel, which also gets heavier, and so on in an infinite cascade. It's a cycle that never ends. You keep adding fuel which keeps getting heavier, requiring even more and more fuel. And you can never reach that final speed because you would need infinite amounts of infinitely heavy fuel. This is essentially what happens when you try to accelerate something to the speed of light. The energy you add to accelerate manifests itself as additional mass according to E equals mc squared, effectively making the object heavier, which makes it even more difficult to accelerate further, creating a feedback loop that makes it impossible to reach the speed of light. And there is an even deeper and more philosophically disturbing consequence of all this that has to do with causality, with the very structure of cause and effect that makes our logical universe comprehensible and habitable. Imagine that you could travel faster than light, that you could send a signal or a ship or any kind of information that travels instantaneously or faster than instantaneously from one point to another in space. Let's think very carefully about what this would mean and why the universe cannot allow this. In special relativity, there is a principle called the relativity of simultaneity, which says that events that are simultaneous for one observer are not necessarily simultaneous for another observer who is moving at a different speed. This may seem abstract, so let me give a concrete example. Imagine you are standing at a train station and you see two lightning strikes at the same time at both ends of the platform. To you, these events are perfectly simultaneous. They happen at the same instant. But now imagine that there is a train passing through the station at high speed, and inside that train there is a passenger observing the same rays. For the moving passenger, the rays do not fall simultaneously. One falls before the other. And this is not because the light from the rays takes different times to reach the passenger, even correcting for the travel time of the light. The events are simply not simultaneous in the passenger's frame of reference. What is simultaneous depends on how you are moving. There is no absolute universal time where we can say that two distant events happen at exactly the same time. Simultaneity is relative, and here is the deep problem this creates. If you allowed faster-than-light travel, if you could send information faster than light, then depending on how different observers are moving, some observers would see the information arriving before it was sent. From their point of view, the information would be traveling backwards in time. And if you can send information into the past, then you can create impossible causal paradoxes that break logic. The classic example, it's the grandfather paradox, where you travel back in time and stop your own grandparents from knowing each other. But then you would never be born. But if you were never born, then you couldn't travel back in time. It's a logical contradiction that has no resolution. Or the simplest paradox yet, you could send a message to yourself in the past saying, "Don't send that message," and what happens then? If you don't send the message, then there is no message from the future, telling you not to send it. So you send the message, but then there is a message from the future telling you not to send is an impossible loop of temporal paradox, and the universe simply cannot allow it. The logic of cause and effect would completely break down. There would be no consistent way to describe what happens, and the elegant and inevitable way the universe prevents these paradoxes is by making it absolutely impossible to travel or send any information faster than light. The speed of light is essentially the speed of causality. It is the maximum speed at which a cause can lead to an effect. It is the speed that keeps the past firmly in the past and the future in the future. It is the speed that guarantees that so always precedes effect, which makes logic possible, which allows us to do science and predict outcomes and live in an understandable universe. Without this fundamental limit, the universe would be a meaningless, chaotic place, where cause and effect would not exist in a coherent way, where temporal paradoxes would be possible, where the very notion of time as an ordered sequence of events would not make sense. And when you think about it this way, you realize that the speed of light is not an arbitrary restriction or a quirk of nature or an annoying limit that prevents us from exploring the cosmos easily. It's an absolute logical necessity. It's a fundamental part of what makes our universe a place where physics makes sense, where we can do experiments and get consistent and reproducible results, where the past determines the future in a causal and predictable way, at least in principle, where reality has structure and order rather than random chaos. Now you're probably wondering about all those science fiction ideas that seem to violate or bypass the speed of light. What about wormholes that connect distant parts of the universe, or warp engines that distort the space around them? Of a ship, or quantum teleportation that appears to send information instantaneously? These things don't violate relativity. Haven't we found loopholes in the laws of physics? Well, let's examine each of these ideas with rigorous scientific care, because the distinction between what is theoretically possible within the known laws of physics and what is definitively impossible is subtle and fascinating. Wormholes are mathematically valid solutions to Einstein's equations of general relativity. They are like tunnels or shortcuts through the fabric of space-time, connecting two points that otherwise they would be very far away. The idea is that you enter one side of the wormhole and come out almost instantly on the other side, which could be on the other side of the galaxy. If you could create and stabilize a wormhole, you could potentially travel enormous distances in very short times without actually traveling faster than light locally. But, and this is a gigantic but with profound implications, there is no evidence that natural wormholes exist anywhere in the universe. We have never observed one. We have never detected indirect evidence of one. They are just solutions, mathematics of the equations that describe how space-time can be curved, and creating one artificially would require something called exotic matter or exotic energy with negative energy density, something that violates certain energy conditions that we think are fundamental. In quantum mechanics, there are effects like the Casimir effect, where you can get negative energy densities in tiny regions of space between very close metal plates. But we are talking about infinitesimal amounts of negative energy on microscopic scales. To stabilize a wormhole big enough for a spacecraft to pass through, you would need enormous macroscopic amounts of negative energy, far more than anything we know how to produce. Or even if it is physically possible to produce, some calculations suggest that you would need more negative energy than all the positive energy in the observable universe, which obviously makes this impractical even if it is theoretically possible. And more importantly, even if you could somehow create a stable wormhole, you wouldn't actually be traveling faster than light in the conventional sense. You would be taking a shortcut through the geometry of space-time. The light would still travel faster than you along any local path through normal space. It's like the difference between walking around a mountain following the winding road versus digging a straight tunnel through the mountain. You get to the other side faster using the tunnel. Not because you are walking faster, but because you are taking a geometrically shorter path. Space-time itself is shortcut, so wormholes, if they existed, would not violate special relativity, which says you cannot travel through space locally faster than light. And how much to the warp drive the idea popularized by Star Trek and other works of science fiction, this is based on a real solution to Einstein's equations proposed by Mexican physicist Miguel Alcubierre in 1994. The ingenious idea is that you compress or contract the space in front of you and expand or stretch the space behind you, creating a bubble or wave in space-time that surfs through the cosmos, carrying your ship along with it. Inside the bubble, you are effectively stationary relative to the space immediately around you, so you don't experience any acceleration and don't violate special relativity, but the bubble itself moves through potentially larger space, is fast that light could travel through normal space. It is an incredibly creative and mathematically consistent idea within general relativity. But again, there are huge practical problems that probably make it impossible. Firstly, you would again need absurd amounts of exotic energy with negative density to create and maintain the warp bubble. Estimates suggest that you would need something equivalent to the mass energy of Jupiter converted into negative energy. Secondly, there are serious problems with causality. If you use a warp drive to do certain maneuvers, you could potentially create loops-closed causal mechanisms that allow time travel into the past with all the associated paradoxes. Third, there are questions about how you would control or direct the bubble once inside it. Some calculations suggest that you could not send signals out of the bubble to control it from within. And once you turned off the warp drive, the accumulated energy in the bubble's horizon would be released in a way that could destroy its destination with high-energy radiation. So while the Alcubierre warp drive is a fascinating mathematical solution of Einstein's equations, turning it into a physical reality faces obstacles that seem fundamentally insurmountable with our current understanding of physics. And even if it worked, it still wouldn't actually be a violation of the speed of light in the local sense. It would be a manipulation of the geometry of space-time itself. And as for quantum entanglement, this bizarre phenomenon, sometimes called by Einstein ghostly action at a distance, because he didn't like it, and spent years trying to prove it wrong, but it ended up being proven experimentally. When two particles are quantumly entangled, measuring the state of one instantly seems to determine or reveal the state of each other, no matter how far apart they are. You can entangle two photons here on Earth, send one to the Moon and one to Mars, and when you measure the polarization of the photon on the Moon, you will instantly know the polarization of the photon on Mars. It appears that information is traveling faster than light between the particles. But, and this is crucial to understanding why it does not violate relativity, you cannot actually use entanglement to send useful information or messages because the results of measurements on each side are completely aleatórios. Você só vê a correlação entre as medições quando compara os resultados depois do fato. E essa comparação tem que ser feita através de canais normais de comunicação clássica que respeitam a velocidade da luz. Imagine que você tem duas moedas mágicas entrelaçadas. Quando você joga uma e ela dá cara, você sabe instantaneamente que se seu amigo do outro lado da galáxia jogar a moeda dele, ela também dará cara. Mas você não pode controlar qual resultado sua moeda dará. É aleatório. Então você não pode usar isso para enviar uma mensagem. Você não pode forçar sua moeda a dar cara para signal something to your friend. Correlation exists but cannot be used for faster-than-light communication. So quantum entanglement is deeply strange and challenges our intuitions about locality and realism, but does not violate causality or allow useful information to be transmitted faster than light. It is as if the universe has carefully designed the laws of quantum mechanics to be as strange as possible while still respecting the fundamental speed limit for information. What all this means for the future of humanity and for our hopes of exploring and colonizing the cosmos and find other intelligent civilizations? This is a question that Neil deGrasse Tyson often contemplates in his talks and books, because the implications are simultaneously inspiring and deeply melancholic. If we are genuinely limited to the speed of light, or at least to speeds far below it, then the universe is an incredibly vast place, huge, isolated, and for the most part eternally inaccessible to us. The Andromeda Galaxy, our closest galactic neighbor, is 2.5 million light-years away. Even traveling at exactly that speed of light, which is impossible for anything with mass, would take 2.5 million years to get there. And during that journey, from the point of view of observers on Earth, you would be seeing the future of the galaxy unfold at accelerated speed due to relativistic effects, but it would still be a journey of incomprehensible length. Most of the other galaxies we see with our most powerful telescopes like the Hubble or James Webb are billions of light-years away. They are completely out of reach forever, no matter how advanced we are. Technology becomes in any imaginable future. The accelerating expansion of the universe is continually carrying distant galaxies rather further away from us. Eventually, faster than light can travel through expanding space. These galaxies are moving beyond our cosmological horizon and will disappear from our sight. Even within our own Milky Way galaxy, the distances are challenging to the point of seeming insurmountable. Our galaxy is approximately 100,000 light-years in diameter. Traveling back and forth at the speed of light would take 100,000 years from the point of view of a stationary observer. And of course, we cannot travel at the speed of light because we have mass. Any manned spacecraft would have to travel significantly slower, even if we managed to build a spaceship that could travel at 10% the speed of light. That would be an extraordinary technological achievement requiring advances in propulsion beyond anything we have today. It would still take 42 years to reach Proxima Centauri, the nearest star, and the astronauts on board would experience some time dilation, but not enough to make a dramatic difference at that relatively low speed. They would return to Earth, having aged perhaps a few months less than the people left behind. A measurable but not transformative difference, and these discoveries have blown your mind as much as mine. Leave a like. Subscribe to the channel and turn on notifications because we have many more mysteries of the universe to unravel together as we continue to explore the limits of human knowledge and physical reality. But here is something genuinely fascinating about time dilation that offers a small glimmer of mathematical hope for long-range space travel, even if it is practically unattainable. If you could somehow build a ship that travels at 99.9% the speed of light or even closer, time aboard the ship would pass drastically slower relative to time on Earth in ways that completely defy our everyday intuition. At 99.9%, the speed of light, time passes approximately 7 times slower. At 99.9%, approximately 22 times slower. At 99.99%, approximately 70 times slower. And as you get closer, arbitrarily close to the speed of light, the time dilation factor grows without limit. From the point of view of the astronauts aboard a ship traveling extremely fast, a journey that takes tens of thousands of years, from the point of view of Earth can be experienced as taking only decades or even years. It is literally a type of one-way time travel into the future. You could theoretically travel to a distant star 1,000 light-years away and return having aged only a few subjective years, while 10,000 years or more would have passed in the Earth. Of course, this means that every civilization you knew would have been gone for millennia by the time you returned. Everyone you loved would have been dead for countless generations. Language and culture itself would have evolved beyond recognition. It would be like returning not just to a different place, but to an alien world that happens to be on the same planet. And building a ship that could reach and sustain such extreme speeds is so far beyond our current technology that we can barely begin to imagine the challenges involved. It would require truly astronomical amounts of energy. Just accelerating a single kilogram of mass to 99.9% of the speed of light requires energy equivalent to detonating several nuclear bombs. An entire ship with crew and supplies, weighing perhaps thousands of tons, would require more energy than all of humanity uses in years. And then you would need to decelerate at the destination, which requires exactly the same amount of energy again, and then accelerate back and decelerate upon returning to Earth, each phase of the journey multiplying the energy requirements. Some theoretical proposals exist, such as solar sails pushed by powerful Earth-based lasers, or fusion engines that consume hydrogen collected from the interstellar medium, or even antimatter engines that annihilate matter and antimatter to release energy with 100% efficiency as E equals mc squared. But all of these ideas are far beyond our current ability to implement, and some may be physically or economically impossible on practical scales. And Neil deGrasse Tyson likes to speculate about alternative approaches that may be more realistic, given the fundamental limits imposed by the speed of light. Perhaps in the distant future, we will develop spacecraft of generation, enormous structures that are essentially self-sufficient floating cities, traveling through interstellar space for centuries, or millennia. Multiple generations of humans would be born, live, and die aboard during the long journey to another star. The descendants that finally reach their destination would be so culturally and genetically removed from the original founders that they would effectively be a new society. Or perhaps we will develop advanced forms of cryonics or animated suspension or hibernation that allow astronauts to essentially sleep during the long journeys, awakening only when they approach the destination. Although keeping human bodies in stasis for centuries without degradation presents enormous biological challenges that still we don't understand how to overcome, or perhaps our consciousness will be uploaded to computational substrates, and we will send robotic ships carrying artificial intelligences or digitized minds that don't care about the length of the journeys because they can simply shut down during transit or operate at accelerated speeds. These scenarios all raise deep philosophical questions about identity and continuity of consciousness, but can bypass some biological limitations. Or perhaps, and this is the most likely possibility given the practical constraints, we will simply accept that manned interstellar travel is beyond our capabilities and focus in sending unmanned robotic probes that can travel for centuries or millennia, collecting data and sending back information at the speed of light. We already do this on a smaller scale within our solar system. The Voyager probes launched in 1977 are now in interstellar space over 20 billion kilometers away. Still sending faint data back to Earth, they will continue traveling for tens of thousands of years, eventually perhaps passing close to other star systems, although they are not aimed at any specific star. In 40,000 years, Voyager 1 will pass less than 2 light-years from the star Gliese 445. If some advanced civilization lives there and detects the obsolete probe, they could retrieve it and examine the golden disk that carries greetings and sounds from Earth. A time capsule of a civilization long gone or transformed beyond recognition. Or perhaps we should focus on sending information instead of physical matter. Radio signals and lasers travel at the speed of light and can carry enormous amounts of information coded. If we discovered an intelligent alien civilization, say 100 light-years away, we could theoretically have a conversation with them, but each message would take 100 years to arrive and each response another 100 years to return. A single exchange of questions and answers would take 200 years. A meaningful conversation would take hundreds or thousands of years to unfold. Entire civilizations could arise, flourish, and fall during the course of a single interesting conversation.